Welcome back, y'all, and today we're going to be solving differential equations with the technique of separation of variables. So what does that even mean? So let's say I had a differential equation. dy by dx is equal to k of x, right? So this is our differential equation, and just to understand what this even means, right? People always see what this is, and they just start automatically going to the formula, the technique, and the way to solve it. And it's easy to solve, but to understand is a little bit more, I say, is the hardest part of mathematics. So what this means is, with every change in x, my solution is going to have a greater rate of change at every point, right? So let's say I had a graph here, right? I had a graph, and basically what we're drawing here is called a vector field. We're trying to draw and approximate and trying to see a visual for what the actual solution looks like. What we're solving for is we're trying to find f of x or y of x. We're trying to solve for f of x. And this f of x has to satisfy this differential. So what that means is if I take the derivative of f prime of x, I should get back k of x. That's what we're basically solving for. So before we start jumping in using our techniques and separation of variables, a great way to kind of see and see if your technique is right is visualize what the solution looks like beforehand. So let's say I had, this is 0, 0, right? And I had a value of x that was 1, okay? So if my value of x is 1, that's going to equal k. So let's just pretend x is 1. My value is going to be k, like this, right? We'll just pretend k is a constant, that's a positive constant. And let's say, just say for now, k has a value of 2. So dy dx is equal to 2x. Okay, great. What does that mean? That means that for every x value of 1, no matter the y. The reason why we're saying no matter the y is because, look at this. This dy dx, this differential equation, is not dependent on y. It's only dependent on x. So no matter what the x value is, no matter what the y value is, the rate of change will stay the exact same if the x value is the same, right? So for example, let's say it was, let's say our point was 2, 0, right here, right? Then our point would be this, and this would be 2, 1. This would also be exactly like this, and this, and this, and this, and this, so on and so forth. Well, let's say I went to 0.40. Well, dy by dx would equal to 2 times 2, which is equal to 4. So I would have rate of change of 4. That means a much steeper slope. A much steeper slope for every y value, as you can see, because our rate of change is only dependent on our x value. It only changes when our x value changes. If our y values change, nothing happens. I could have 4, 4, and if I plug in all those numbers to my differential, to my derivative, I would still get back 4. Or, sorry, this is 4, so then this would be 8. I would still get 8. A much steeper slope. So how do we solve for a differential like this? Well, that's a pretty good question. I'm here to solve for you guys. So how we solve this equation is we use the idea of separating the variables. What does that even mean? So separating the variables means is we can treat these terms algebraically, which means I can multiply this entire side by dx to get rid of it. You just treat it like a fraction, like a variable. And so basically step 1 is dx equal to 2x. Step 1 is separate the differential, or split the differential, slash split the differential, right? You want to get these differentials on either side. So you want to get all the x's. So what is it? Oh, like terms together, right? So all the x's on one side and all the y's on one side, right? So as of right now, we can see that there's no y's, right? So we don't have to change anything, but we do see that there's an x on this side and x on this side, and we want to get those together. So what's the best way to do that? Well, what I'm going to do is I'm going to multiply each side by dx, right? So if I multiply this side by dx, this cancels out, and now I'm left with dy is equal to 2x dx. All right, that's great. Now what do we do here? Now what we're going to do is we're going to integrate both sides and find the antiderivative. Sorry for my very, very bad handwriting, but hopefully you guys understand the point I'm trying to get across. So now I'm going to integrate, right? So I'm going to integrate on this side, and I'm going to integrate on this side with respect to their differential, right? So on this side, I'm integrating with respect to dy, and on this side, I'm integrating with respect to dx, right? So on this side, let's try this one. Let's integrate each side by itself individually, right? Basically, what I'm doing is I'm integrating a y0 with respect to dy. And the reason why I put this y0 is we can true right in front of us here, in front of this one is kind of a invisible one, right? Well, if we want to get a 1, we can also treat that as y0, right? So what I'm going to do is I'm going to take the antiderivative of y to the 0th power, which is going to be just y, right? Because y to the 0th power, if I integrate that, well, I'm going to add 1 to this, and then I'm going to divide by 1, right? I add n plus 1 divided by n plus 1. So basically what that's going to be is y to the 0 plus 1, 1 plus 0. All right, I'll do 0 plus 1 just for symmetrical purposes, 0 plus 1. Right, so that's going to give me y. So that's the antiderivative of y to the 0th power. But remember, since we're also we're trying to find the general solution. We don't have a specific solution. This is a non-definitive integral. I think that's the proper vocabulary. Please correct me if I'm wrong. I believe that's the proper vocabulary. Basically, since it is a non-definite integral, we have to do a plus e, a constant, right? And I'm just going to do plus c of 1. Okay, so now on this side, we're going to take the integral, the antiderivative. Well, what's the antiderivative of 2x? Well, we know that right now it's 2x to the 1 power. So what I'm going to do is remember our antiderivative rules of x to the dx is equal to, what was it? X to the n plus 1 over n plus 1, right? X to the n power. Ah, that's the formula. Sorry, I just remembered. Usually, when you keep doing calculus, it becomes in such a way that you kind of forget the basics. So basically, the integral of x to the n power with respect to dx is equal to x to the n plus 1 over 1 n plus 1, right? So 2x is 1 to the 1 power, so then I'm going to do n plus 1 divided by 1 plus 1, and that gives us x squared. So this is going to be x squared plus c2, right? I'm going to do my second constant. And basically what I'm going to do is I'm going to minus on both sides just to simplify it a little bit. And I get y is equal to x2 plus c3, and c3 is equal to c2 minus c1. But in the end, you're going to find that the constants don't really matter unless you're given an actual solution. For example, let's say I was given that f of 0 is equal to 4. If I was given f of 0 is equal to 4, and I have my general solution here, I could just plug my values that I know and solve for the constant. So we know that 4 is equal to x squared 0 squared plus c3, which means c3 is equal to 4. So my function is going to be y is equal to x squared plus 4. And now what's the greatest thing now? Not the greatest thing is, but to make sure we check our answer, and the best way to understand, and basically the whole point of solving a differential equation, is to see if our solution that we found satisfies our original differential equation. So we know that if we took the derivative of this function right here, it should get us back to dy dx is equal to our original differential equation, 2x. So I took the derivative right now on both sides, right? D by dx of y is equal to d by dx of x squared plus 4. Well, we know the derivative of y with respect to x is just dy over dx, and the derivative of this side with respect to x, well, we know the derivative of this would just be 0, and this would be 2x. And as you can see here, our answer and our final solution satisfies our differential equation. Thank you very much. Have a good day.